Tech in 5.
Ever wondered how top tech companies evaluate coding skills in interviews? Mastering coding challenges is your key to securing that dream tech job. Do you want to know how to validate a winning Mahjong hand programmatically? You're in the right place. By the end of this video, you'll be able to solve it in a coding interview. Mahjong, with its variety of tiles and regional rules, can seem complex. However, in a typical coding interview, it will be simplified to numbers 1 to 9. The rules for a winning hand are also simplified in the coding interview version. A winning hand includes 4 sets plus 1 pair. A set could be a pung, which is 3 identical tiles, or a chow, which is a sequence of 3 consecutive numbers. And a pair? That's simply 2 identical tiles. Let's dive into how we can validate these winning combinations in code. At first glance, the solution appears straightforward. We could sort the tiles and iterate through them, identifying pairs, pungs, and chows. The challenge, however, lies in the fact that a single tile may fit into multiple sets. If we swap out a tile in our example, the hand might not look like a winner with our solution. Yet, it can still form a winning combination. This is why this question is difficult, because it requires an approach that initially meets the eye. Let's explore how we can account for this complexity in our solution. To tackle a tough problem, breaking it down into smaller, manageable pieces often helps. For example, removing a pair of 1s from our hand, does this leave us with only sets? If that doesn't work out, what if we remove a pair of 2? Then we'd reassess the remaining tiles to see if we're left with a winning hand. Let's dive right in. We start with converting the tiles to a count set. First, try to identify the pair. If we haven't yet formed a pair in our hand, our algorithm will attempt to create one. To ensure that we're not altering the count set, in case we need to roll back, we will create a copy of the count set. Once we've potentially identified a pair, we'll invoke our recursive function, signaling that a pair has been formed, by passing an updated argument. Now, if this tentative pair doesn't lead us to a winning hand further down the recursive path, we simply continue exploring other possibilities, by trying to form a pair with the next available tile. Next, let's consider the formation of pungs, which are sets of 3 identical tiles. Our algorithm takes a similar tack here. We generate a fresh copy of the count set for each recursive call, and proceed to decrease the count of the current tile by 3. With each attempt to form a pung, we make a recursive call with an increased set count. However, if a particular pung doesn't contribute to a winning combination, we proceed to the next tile, and repeat the process. The most nuanced part of our algorithm deals with the formation of chows, which are sequences of 3 consecutive numbers. We must ensure that we have at least one of each tile necessary to form a sequential run. If we find such a sequence, we again make a copy of the count set, decrease the counts for the tiles in the sequence, and call our recursive function with an updated set count. As we attempt to form chows, if we discover that a sequence doesn't lead us to winning hand, we continue iterating, looking for other sequential opportunities that could contribute to a winning hand. This algorithm explores all possible paths. If we manage to form the requisite 4 sets in 1 pair, return true indicating the winning hand. Once we have the algorithm figured out, the coding part is straightforward. The only part worth noting is the addition of a visited set, which is important in optimizing the solution by preventing repeated work on the same configurations of the hand. Before making a recursive call, we check if the current count set has already been visited. If it has, we can skip the recursive call for this set. When a count set is about to be used in a recursive call for the first time, we add it to the visited set. Since count sets are mutable and cannot be directly added to a set, we will need an immutable representation of them. A simple way to do this is to convert the count set to a frozen set or a tuple, which can be added to the visited set. The time complexity of the recursive solution is dependent on the number of possible subproblems it needs to solve. In the worst-case scenario, the function could potentially explore all permutations of the tiles, leading to a factorial time complexity in terms of the number of tiles. By adding a visited set, we aim to eliminate redundant work by caching the results of subproblems. This means that the time complexity can be significantly reduced. However, in our specific scenario with fixed 14 tiles, the time complexity is actually constant, both with and without the visited set. So does the space complexity. We've delved into one effective solution here, but there are certainly other strategies. Got a different solution? Feel free to share your ideas in the comments.
Stay tuned for more videos on Tech in 5.